Right, time for a super quick homework hint on problem of rotational motion of a falling chimney. This is problem 67 out of chapter 10. So first of all, some terminology just to clear up and remind you. So there's rotational acceleration, which is alpha, right? So that's going to be radians per second squared. Then we have radial acceleration, which here I've called a sub c. That's also known as centripetal acceleration. So we've known about that for a while. And then there's the tangential acceleration, a sub t. So the centripetal acceleration, if we were to draw it on this picture, the centripetal acceleration points back toward the center, and the tangential acceleration would point tangent. Okay, so that's the points where we're being asked to find these accelerations. Now the radial acceleration, or the centripetal acceleration, as always, this is v squared over r, which, if we want to write that in terms of omega, is omega squared r. And the tangential acceleration is found, if you know alpha and you multiply it by r, that'll give you the tangential acceleration. So that gives us a hint of what concepts we want to bring into play when calculating these, right? So if we want to know a velocity, just like with translational motion, we want to think about doing conservation of energy, right? We don't want to do kinematics because as this thing falls, the acceleration is going to be constantly changing. For the tangential one, we need to find alpha first, so that's going to require us to find a torque. So we can find the torque at this point, then calculate alpha, and then that'll give us the ability to calculate the tangential acceleration. Now, in this problem, the force that's happening is the force of gravity. Now, the force of gravity we can think of as acting. It won't act on the end of the object. It'll act at the center of mass, right? So when you're calculating your torque, you want to find the radius that you should use would be this r, which is going to be half the length of the chimney. But then when you're calculating the moment of inertia and when you're calculating these accelerations, you're looking at a point at the top of the chimney, so you should use those. Now, of course, the torque, when you find the torque here, this gravity points down, but you need the part that's tangential to the chimney. And then also in the part where when you're looking for the radial acceleration, when you're doing conservation of energy there, so again, this is, we're talking about gravity. Gravity acts at the center of mass. So when you're doing a change in height, it's going to be the change in height from what you started with of the center of mass, right? So that's the change in height that should go into that. Keep those things in mind as you go about it, right? So that's kind of a hint to get you started and what you're looking for and what concepts to bring. So you're going to have to do both a conservation of energy problem and a torque problem. And another thing that you can reference is in the textbook, sample problem 10-12 deals with a similar situation. So you can check that out for some help there.